Today we will talk about the alternate segment theorem. Before we go into the details and proof of this theorem, let's understand a bit more about segments. In this diagram, chord BC divides this circle into two regions which are called segments. The bigger region, which is called the major segment, and the smaller region, which is called the minor segment. Now, let me take a point D on the circumference of the circle and connect BD and DC. Angle BDC now becomes an angle of the major segment. Let me take another point E and connect BE and BC. Angles BDC and BEC are two angles in the same segment, and as proved earlier, they are equal. Now let's take a point F in the minor segment and connect BF and CF. Now angles BDC and BFC are two angles in the different segments, and we will see later that they are supplementary. As we can see, chord BC is splitting the circle into two segments. Let's call them 1 and 2. Chord BC also intersects tangent DE, forming an angle BCD, which we will call X. Angle X is located in segment 1. The alternate segment theorem states that if I take any angle in segment 2, for example, angle BFC, then these two angles will be equal. Similarly, if I take angle BCF, which is in segment 2 as Y, and I pick a point G in segment 1, then this angle must also be Y. Let's prove this. I have redrawn this diagram to make it easier to visualize. We have to prove that angle EBD is equal to angle EFB. In order to prove this, let me connect the center of the circle A to point E and B. And let me take angle EBD as X. As you can see, I have connected AB and AE to prove this theorem. I will also take angle EBD as X. Now, we know that AB is the radii of the circle and CD is the tangent. And we also know that the radii and the tangent intersect at 90 degrees. That means this angle has to be 90 minus X. Now, because both AB and AE are radii, angle AEB also has to be 90 minus X. The sum of degrees in a triangle is 180. That means angle EAB is equal to 180 minus 180 minus 2x. Rewriting this, we get, and this is equal to 2x. So, angle EAB equal to 2x degrees. And now look at angle AEAB. It is the angle subtended at the center, and the angle we want to find, EFB, is the angle at the circumference. Because the angle at the center is always twice the angle of the circumference, we know that angle EFB has to be half of 2x, that is x. So, we have proved that EBD is equal to EFB. Now in this theorem, we're going to talk about what is a cyclic quadrilateral. A cyclic quadrilateral is like quadrilateral EDCB, in which all the points are on the circumference of the circle. Let's see a few more examples. In this diagram, we have a cyclic quadrilateral because all the points are touching the circumference of the circle, and we can see that the blue angles add up to about 180 and the red angles also add up to about 180. Now if I move this point around the circle, you can see that the blue angles still always add up to 180. But when I move this point outside the circle, you can see that the two angles don't add up to 180 anymore. Let's see why. We have to prove that angle BED plus angle BCD is equal to 180 degrees. As you can see, I have connected points B and A and D. Let angle BED be X and angle BCD be Y. As you can see, we have angle BAD, which is the angle at the center for the arc BD, and the same arc BD subtends the angle BED at the circumference. By the previous theorem, we know that the angle subtended at the center has to be twice the angle subtended at the circumference. That means BAD has to equal 2x. In the same way, if you turn the figure upside down, you'll find out that the angle Y is an angle at the circumference for the major arc BD, and that the reflex angle BAD is the angle at the center for the same arc. That means angle BAD reflex has to equal 2y. Because angle BAD, both of them are angles around a point, their sum has to equal 360. After factoring the 2 out, we get 2 into x plus y equal to 360. And finally, after dividing by 2 on both the sides, we get x plus y equal to 180.